Hello learners, once again I welcome on the class of fluid mechanics. So I hope you all are safe and doing well. So in the previous discussion we have seen the fluid dynamics, and in fluid dynamics I have discussed the Bernoulli's equation in terms of Bernoulli's equation per unit weight, in terms of Bernoulli's equation per unit mass, and in terms of Bernoulli's equation per unit volume. So today I will discuss the Bernoulli's equation in pipe flow. We will see how to apply the head loss in the pipe flow, and after that I will show you the application of kinetic energy correction factor, and after that I will discuss what is kinetic energy correction factor and momentum correction factor, and after that I will show you the value of kinetic energy and momentum correction factor for laminar and turbulent flow, and when our velocity distribution will vary like parabolic distribution, logarithmic distribution, and ideal fluid flow or uniform velocity distribution. After that I will discuss the devices used for the measuring discharge like Venturi meter, orifice meter. So today I will discuss the Venturi meter. So today I will discuss about the energy equation applied in the viscous fluid flow or pipe flow. Energy equation applied in viscous fluid flows or pipe flows. Let us consider this is our pipe. Two section I have taken, one and 2. So pipe flow are highly viscous flow. Pipe flows are highly viscous flow. In the direction of pipe there will be loss of energy. In the direction of pipe flow there will be energy loss. Pipe flows are only possible from high total head to low total head condition. The flows are possible only from high total head to low total head. So if I write the Bernoulli's equation, according to Bernoulli's equation at 1 and 2, so we can write P1 by gamma plus V1 square by 2G plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z2 plus there will be head loss. So this is the Bernoulli's equation per unit weight, where all the symbols we have already discussed in the last class. P1 by m gamma is pressure head, V1 square by 2G is the static head or kinetic head or velocity head, Z1 is the potential head or datum head, HL is the total head loss. HL is the total head loss. We can also write this Bernoulli's equation in terms of kinetic energy correction factor, and so if I write this Bernoulli's equation per unit weight in terms of kinetic energy correction factor. So what is kinetic energy correction factor and what is the use of this kinetic energy correction factor in the Bernoulli's equation? So if I will discuss about the real fluid, velocity head will not be constant throughout the cross section of the conduit. So if we want to calculate the actual kinetic energy in terms of average velocity, so we will have to multiply average kinetic energy correction factor, that is called kinetic energy correction factor. So actual kinetic energy is alpha times 1 by 2 m into average velocity whole square. So if we consider a real fluid, velocity head v square by 2g will not be constant throughout the cross section. If I draw the velocity distribution in real fluid and ideal fluid, so this is our velocity distribution in the real fluid. Velocity distribution in real fluid. How it will come? So these things I will discuss in the pipe flow. So this is the velocity distribution in the real fluid, and if I talk about the velocity distribution in ideal fluid, so it is like that, constant throughout the cross section. Velocity distribution in ideal fluid. So these are the velocity distribution in the real fluid and in the ideal fluid. So if we want to calculate, actual kinetic energy in terms of average velocity, so we will have to multiply average kinetic energy by a factor alpha called kinetic energy correction factor. So what is the expression of kinetic energy correction factor? So this kinetic energy correction factor can be computed as VQDA divided by A into V average whole cube. So this is the expression to compute the kinetic energy correction factor, where V average is equal to V into dA. Alpha is the kinetic energy correction factor. For circular pipe flow, this value is 2, and for flow between parallel plates, the value is 1.543. But these two value is valid for the laminar flow. For turbulent flow for the circular pipe, alpha is 1.0 to 1.06, and for ideal flow for all types of pipe, it will be the 1. So if I write the value of kinetic energy correction factor, so parabolic profile as laminar flow. So alpha is 2 for circular pipe, for circular pipe, and for parallel plates, for parallel plates the value of alpha is 1.543. But remember in mind that this value is valid for the laminar flow and our velocity distribution should be parabolic. Is the velocity distribution is logarithmic and flow is turbulent. Then in such case the value of alpha is 1.0232 to 1.06 in case of circular pipe. In case of ideal flow, or velocity distribution is uniform, the value of alpha is 1 for all pipes. So these are the velocity distribution, this value of kinetic energy correction factor. So if I apply this application of this kinetic energy correction factor, so let us assume this is our two section first, and these are the section second, 2. So if I apply the kinetic energy Bernoulli's equation, so applying Bernoulli's equation at 1 and 2. So if I apply the Bernoulli's equation at 1 and 2, so we can write P1 by gamma plus alpha 1 into V1 square by 2g plus Z1 is equal to P2 by gamma plus alpha 2 V2 square by 2g plus Z2 plus head loss at 1, 2. So these are the Bernoulli's equation if I consider the kinetic energy correction factor. P1 by gamma plus alpha 1 V1 square by 2g plus Z1, where P1 by gamma is the pressure head at section 1, V1 square by 2g is the velocity head or kinetic head or static head at section 1, and Z1 is the datum head at 1. Similarly, pressure head at 2, velocity head at 2, potential head or datum head at 2, and head loss between 1 to 2. And alpha 1 is the kinetic energy correction factor at section 1, and alpha 2 is the kinetic energy correction factor at section 2, where head loss HL12 is the head loss between 1 and 2. A similar parameter momentum correction factor is defined in momentum equation, and this it is denoted by beta is equal to integral of V square dA divided by A into average velocity whole square. So this is the expression of momentum correction factor, where V average is equal to VDA divided by area. So with the help of that, we can compute the momentum correction factor. So now I am going to discuss about the application of energy equation. And application of energy equation, firstly I will discuss the Venturi meter. So Venturi meter is a device used to find out the discharge through a pipeline, or it is also defined as it is a converging diverging tube, which is basically used to measure the flow rates of fluid running through pipe. So this device is used to measure discharge through a pipe. It is a converging diverging device. Which is basically used to measure the flow rates. So if I draw a Venturi meter, this is our device. If I take the section, so this section is called section first, and this is called the normal section. And this section is called throat section. This angle is called converging angle, and this angle is diverging angle. So diverging angle is generally 5 to 6 degree, and converging angle is 22 degree. So if I apply the Bernoulli equation, according to Bernoulli equation, P1 upon gamma plus V1 square by 2G plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z2. So we can write P1 by gamma plus Z1 minus P2 by gamma plus Z2 is equal to V2 square by 2G minus V1 square by 2G, and P1 by gamma plus Z is the piezometric head. So we can write this is the difference in piezometric heads between normal section and throat section, and this difference can be written as H is equal to V2 square minus V1 square by 2G. Or if I write in terms of discharge, so we can write Q square 1 by A2 square minus 1 by A1 square divided by 2G. So Q is equal to, we can write A1 A2 divided by square root of A1 square minus A2 square times root under 2GH. So this is our theoretical discharge in our Venturi meter. Theoretical discharge in our Venturi meter. So here Q theoretical is a theoretical discharge as we neglected losses. As you have seen that when I applying the Bernoulli equation, I have neglected the head loss between 1 and 2. A1 is the area, cross-sectional area at the normal section, and A2 is the cross-sectional area at the throat section. In terms of ratio, this A1 by A2 is called area ratio. A1 by A2 is the area ratio. The ratio of actual discharge to the theoretical discharge is called coefficient of discharge, and it is denoted by CD. So we can write CD is equal to Q actual by Q theoretical, or we can write Q actual discharge is the CD times Q theoretical, or Q actual is equal to CD A1 A2 square root of 2GH divided by square root of A1 square minus A2 square. So this is the expression of actual discharge in the Venturi meter, where A1 A2 divided by square root of A1 square minus A2 square into root under 2G is called Venturi constant. Venturi constant. A1 into A2 divided by A1 square minus A2 square into root under 2G is called Venturi constant. So I have written, as I told you earlier, that in Venturi meter convergence angle is taken as 22 degree and divergence angle of divergence angle is taken as 5 to 6 degree. Let d be the diameter of, small d be the dia of throat, and capital D be the diameter of pipe. So diameter of throat approximately written as 1 by 3 to 3 by 4 times the diameter of pipe, or normally D is equal to half the diameter of pipe, we can also write. So variation of coefficient of discharge with losses. So I will talk about the coefficient of discharge. What is the value of coefficient of discharge? Coefficient of discharge, CD. So the value of coefficient of discharge in Venturi meter when flow separation does not occur is 0.98. The value of in Venturi meter, the value of CD is 0.98. The value of coefficient of discharge will value with the different devices. Like if I discuss the orifice meter after that, so the value of coefficient of discharge will be different. So the value in case of Venturi meter, it is taken as 0.98, and the condition is that when flow separation does not occur. Variation of coefficient of discharge with losses. So if I apply the Bernoulli equation with head loss, so P1 by gamma plus V1 square by 2G plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z2 plus HL. Or we can write P1 by gamma plus Z1 minus P2 by gamma plus Z2 is equal to V2 square minus V1 square by 2G plus HL. And this piezometric difference between 1, 1 and 2, 2 is H. So H minus HL is equal to V2 square minus V1 square by 2G. Or we can also write H minus HL is equal to 1 by 2G Q square by A2 square minus Q square by A1 square. So Q square is equal to A1 square A2 square 2G H minus HL divided by A1 square minus A2 square. So the actual theoretical discharge is equal to A1 A2 root under 2G H minus HL divided by square root of A1 square minus A2 square. So this is the theoretical discharge when I will consider the head loss. So actual discharge is CD times actual discharge is equal to CD into A1 A2 root under 2G H minus HL divided by square root of A1 square minus A2 square. And if separation occurs, it leads to loss of energy and in this case the value of CD is very less, very less. So the actual discharge can be written as A1 A2 square root of 2G H minus HL divided by square root of A1 square minus A2 square. And if I write the actual discharge, if I computed in the Venturi meter, A1 A2 square root of 2GH divided by square root of A1 square minus A2 square. So if I equate these two actual discharge, so the coefficient of discharge CD is also, so CD is equal to square root of H minus HL divided by H. So this is the expression of coefficient of discharge when I consider the head loss in the Venturi meter. So dear student, today I have discussed the Bernoulli equation in pipe flow, and we have seen the Bernoulli equation at two sections. I have applied P1 by gamma plus V1 square by 2G plus Z1 is equal to P2 by gamma plus V2 square by 2G plus Z2 plus head loss, where we have already discussed the P1 by gamma is the pressure head, V1 square by 2G is the velocity head, and Z1 is the potential head or datum head at section 1-1. Head HL is the head loss between 1-1 and 2-2. And after that I have discussed the kinetic energy correction factor alpha, and the expression we have written VQ into dA divided by A into V average Q, where V average is equal to V into dA divided by A. And after that I have discussed the kinetic energy correction factor value for laminar, turbulent and ideal fluid flow, and we have seen the value of for the laminar and turbulent flow when our velocity distribution is parabolic, logarithmic and uniform flow. And after that I have also discussed the what is the expression of momentum correction factor, and after that I have discussed one devices. With the help of that device we can use the discharge, that is Venturi meter. So in the Venturi meter we have seen the expression of theoretical discharge, that is A1 A2 square root of 2GH divided by square root of A1 square minus A2 square, and the expression of actual discharge, that is CD times A1 A2 square root of 2GH divided by A1 square minus A2 square, where CD is the coefficient of discharge, that is the ratio of actual discharge to the theoretical discharge, and this value is generally 0.98 for the Venturi meter if our flow is not separated. Similarly, A1 is the cross-sectional area at section 1-1 and A2 is the cross-sectional area at the throat section. And after that I have discussed what is the converging angle and diverging angle in the Venturi meter. So in the next class I will discuss the expression of H when our Venturi meter is inclined, when our Venturi meter is inverted, and after that I will discuss the orifice meter and I will derive the expression of discharge in orifice meter. So take care of your health and happy learning.